When dealing with a 208 volts power source to operate 230 volts fountain motors controlled by a panel with a 120 volts time clock, you have a couple of options to consider. One is using a boost transformer in conjunction with an isolation transformer, and the other is using separate boost transformers for each motor. Supplying the neutral from the 208 volt source straight through to the controller panel is generally acceptable, but with added isolation. It is generally acceptable to supply the neutral from the 208 volt source straight through to the controller panel. However, since the controller panel has a 120 volts time clock, you need to ensure that the neutral from the 208 volt source is isolated from the neutral of the motor loads. This is necessary to prevent ground loops and potential electrical hazards. To achieve this isolation, you can use an isolation transformer between the 208 volt source and the controller panel. An isolation transformer provides a separate neutral that is isolated from the primary neutral. The basic wiring diagram involves the 208 volt source feeding the isolation transformer, which then feeds the controller panel, which in turn supplies power to the 230 volts motors. The advantages of this approach firstly include providing isolation between the 208 volt source and the controller panel, preventing ground loops, and secondly allows for the use of a single boost transformer for all three motors. The disadvantages primarily involve the need for an additional isolation transformer, which increases both the cost and complexity of the system. As an alternative to using an isolation transformer, you can install separate boost transformers for each of the motor loads. This method eliminates the need for neutral isolation, but requires the use of multiple transformers. The wiring for this setup includes the 208 volt source feeding a boost transformer, which then powers a 230 volts motor, and this configuration is repeated for each of the three motors. The advantages of using separate boost transformers firstly include eliminating the need for neutral isolation, and secondly, it can be a relatively simple and cost-effective approach. The disadvantages are that it requires multiple boost transformers and may not be as compact a solution as using a single isolation transformer. In conclusion, both methods are viable, and the best choice will depend on your specific needs and budget. If isolation between the 208 volt source and the controller panel is critical, the isolation transformer approach is recommended. However, if cost and simplicity are more important, the separate boost transformer approach may be more suitable. Now let's delve a bit deeper into the technical aspects of each option. Firstly, the isolation transformer approach. An isolation transformer is designed to provide electrical isolation between two circuits. It does this by using separate primary and secondary windings that are not electrically connected. The only connection between the two windings is magnetic. This isolation helps to prevent ground loops, which can cause unwanted noise and interference in electrical systems. Ground loops occur when there are multiple paths to ground, creating a loop in the ground wiring. This loop can act as an antenna, picking up electromagnetic interference and injecting it into the electrical system. The isolation transformer breaks this loop, preventing the flow of unwanted current. When selecting an isolation transformer, it is important to choose one that is rated for the appropriate voltage and current. The transformer must be able to handle the input voltage from the 208 volt source and provide the necessary output voltage for the controller panel. It must also be able to handle the current drawn by the controller panel and the motors. The isolation transformer should also be sized appropriately for the load. It is generally recommended to choose a transformer that is rated for at least 125% of the load to account for any inrush current or other unexpected surges. Secondly, the separate boost transformer approach. A boost transformer, also known as a step-up transformer, is designed to increase the voltage of an electrical signal. In this case, it is used to increase the 208 volts from the source to the 230 volts required by the motors. When using separate boost transformers for each motor, it is important to ensure that each transformer is sized appropriately for the motor it is powering. The transformer must be able to handle the motor's starting current, which can be significantly higher than its running current. It is also important to ensure that the transformers are properly grounded to prevent electrical hazards. When selecting boost transformers, it is important to consider the voltage regulation of the transformer. Voltage regulation is a measure of how much the output voltage of the transformer changes as the load changes. A transformer with good voltage regulation will maintain a relatively constant output voltage even as the load varies. This is important for ensuring that the motors receive the correct voltage at all times. Another important factor to consider is the efficiency of the transformer. The efficiency of a transformer is a measure of how much of the input power is converted to output power. A more efficient transformer will waste less energy, which can save money on electricity bills. It is also important to consider the size and weight of the transformers. If space is limited, it may be necessary to choose smaller, more compact transformers. However, smaller transformers may not be as efficient or have as good voltage regulation as larger transformers. The choice between the isolation transformer approach and the separate boost transformer approach will depend on a number of factors, including the cost of the transformers, the available space, and the importance of electrical isolation. If electrical isolation is critical, the isolation transformer approach is the better choice. However, if cost and space are more important, the separate boost transformer approach may be more suitable. The 120-volt time clock in the controller panel requires a neutral connection to operate correctly. The neutral wire provides a return path for the current flowing through the clock. Without a neutral connection, the clock will not be able to function. When using a boost transformer, the neutral wire from the 208-volt source can be connected directly to the neutral terminal in the controller panel. However, when using an isolation transformer, it is important to ensure that the neutral wire from the 208-volt source is isolated from the neutral wire in the controller panel. This can be achieved by using a separate neutral wire for the controller panel, which is connected to the neutral terminal on the secondary side of the isolation transformer. This separate neutral wire will be isolated from the neutral wire on the primary side of the transformer, preventing ground loops and other electrical hazards. It is also important to ensure that all of the wiring is done correctly and in accordance with all applicable electrical codes. Incorrect wiring can be dangerous and can damage the equipment. It is always recommended to consult with a qualified electrician before making any electrical connections. The electrician will be able to ensure that the wiring is done safely and correctly and that the equipment is properly grounded. In addition to the above considerations, it is also important to consider the environmental conditions in which the equipment will be operating. If the equipment will be exposed to moisture or other harsh conditions, it may be necessary to choose transformers that are specifically designed for outdoor use. These transformers are typically enclosed in a weatherproof enclosure to protect them from the elements. It is also important to ensure that the equipment is properly ventilated to prevent overheating. Overheating can damage the transformers and other electrical components. Proper ventilation can be achieved by providing adequate airflow around the equipment. This may involve installing fans or other cooling devices. Finally, it is important to regularly inspect the equipment to ensure that it is in good working order. Any damaged or worn component should be replaced immediately. Regular maintenance can help to prevent problems and extend the life of the equipment. To recap, firstly, determine the total power requirements of the motors and the control panel. This will help you select appropriately sized transformers. Secondly, carefully consider the need for electrical isolation. If ground loops are a concern, an isolation transformer is the best option. Thirdly, if cost and simplicity are priorities, separate boost transformers for each motor may be more suitable. Fourthly, ensure that all wiring is done in accordance with local electrical codes. Consult a qualified electrician if you are unsure about any aspect of the installation. Fifthly, provide adequate ventilation for the transformers to prevent overheating. Sixthly, regularly inspect the equipment for any signs of damage or wear. Addressing the specific question of whether it is okay to supply the neutral from the 208-volt source straight through to the controller panel, the answer is generally yes, but with precautions. Specifically, you need to ensure isolation. Using an isolation transformer is a common method to achieve this. It is also essential to properly ground the system to prevent electrical hazards. Grounding provides a low impedance path for fault currents, which helps to protect people and equipment from electrical shock. The grounding system should be designed and installed in accordance with all applicable electrical codes. When working with electrical equipment, it is always important to take safety precautions. Wear appropriate personal protective equipment, such as gloves and safety glasses. Be sure to energize the circuit before making any connections. And if you are not comfortable working with electrical equipment, consult a qualified electrician. Regarding the choice between a single larger boost transformer versus multiple smaller ones, there are trade-offs. A single larger transformer might be more efficient and potentially less expensive overall, but it lacks redundancy. If it fails, the entire system is down. Multiple smaller transformers offer redundancy. If one fails, the other motors can still operate. Also, smaller transformers are easier to handle and install. However, the combined cost of multiple smaller units could be higher. Consider the long-term operational needs and maintenance aspects when deciding. Another factor often overlooked is the inrush current of the motors. Motors draw a significantly high current when starting them when running at their normal speed. The transformers must be sized to handle this inrush current without excessive voltage drop, which could prevent the motors from starting properly. Check the motor manufacturer's specifications for inrush current requirements. Also, consider the ambient temperature where the equipment will be located. Transformers are less efficient at higher temperatures, and their capacity decreases. Direct the transformer's capacity accordingly if it will be operating in a hot environment. In summary, the decision of how to power the 230 volts fountain motors from a 208 volts supply involves careful consideration of electrical isolation, transformer sizing, wiring practices, safety precautions, and environmental conditions. Consulting with a qualified electrician is highly recommended to ensure a safe and reliable installation. Also note that some motors are designed to operate within a range of voltages, such as 220 volts to 240 volts. If your motors fall into this category, they may operate acceptably on 208 volts without a boost transformer. However, it is important to check the motor manufacturer's specifications to ensure that this is the case. Operating a motor at a voltage below its rated voltage can reduce its performance and lifespan. If you choose to operate the motors at 208 volts without a boost transformer, it is important to monitor their performance closely to ensure that they are not overheating or experiencing other problems. This includes checking the motor's operating temperature and current draw. If the motor is running hotter than normal or drawing excessive current, it may be necessary to install a boost transformer. Finally, remember to keep detailed records of all electrical work performed, including wiring diagrams, transformer specifications, and test results. This will be helpful for troubleshooting any problems that may arise in the future and for ensuring that the equipment is properly maintained.